So now we begin the next section in which we will see how to set up the discrete phase model. We will study one by one each step involved in the entire problem setup of the discrete phase model. First step, we import the mesh and check the mesh. That is, we go into problem setup, then click on general, and then we can check the mesh here, the mesh that we have imported. We scale the domain, that is, we set the bounding dimensions of this domain, whether the dimensions are correct and whether units of that are correct. We select the solver, whether we are using pressure based or density based. We select the velocity formulation. We also select whether we are solving a steady state problem or a transient problem. The step 2 is to turn on our discrete phase model. For this, we go into problem setup, models, and then click on discrete phase. Initially it is off, then the discrete phase model panel or the window will pop up, and here you can turn on various options that are related to discrete phase model. The first among them is interaction with continuous phase. You can click it on or off. You can also turn on the unsteady particle tracking. Under tracking, you can give the maximum number of steps in which the discrete phase particles will be tracked and also specify the length factor. So this is how you turn on the discrete phase model. The next step is to do various settings or options that are related to discrete phase model. You can turn on unsteady particle tracking. Then this whole section will elaborate more, and you have to give different unsteady particle tracking parameters as well. We will see all these in detail in the coming slides. You will also need to give the tracking parameters for steady state tracking as well. Interaction with continuous phase means that the steady state particles will interact with the continuous phase, that is, exchange mass, momentum, and energy. You can turn this on if you need to. You can also specify tracking parameters and select the drag law. There are various types of drag laws available, like spherical, non-spherical, Stokes-Cunningham, and high Mach number. You can select the drag law depending upon your requirement or the physics involved. You have to give the number of continuous phase iteration per dpm iteration as well. That is, how many number of continuous phase iterations will be done for one dpm iteration. The next tab is the physics model tab. In this tab, we can turn on the different physical submodels which are applicable to our particular problem. The various physics that we can include are thermophoretic force, Brownian motion, Safman lift force, erosion and accretion phenomenon, as well as two-way turbulence coupling. We can also turn on droplet collision and droplet breakup and give various parameters related to it. We will see the parameters of all these submodels in detail in the coming slides. Just remember, we can include all these phenomena, all this physics into our discrete phase model. The next step is to set up the various numerical options related to the discrete phase model, that is, accuracy related options like accuracy control, tolerance, maximum refinement, coupled heat and mass solution, and track in absolute frame. We can also turn on higher order schemes for tracking like trapezoidal, and also lower order schemes like implicit. So this is all related to the numerical parameters or numerical accuracy related to the discrete phase model. This controls the accuracy of our solution. Now the step 7 is to define discrete phase injection. Till now we have only defined the discrete phase model, but from where do our discrete phase is injected or comes into the domain? We have to define that by clicking on injection. Then a injection properties panel will open up, and we define various types of injection in this. We can create new or edit or delete. We have to give different parameters like initial velocity, initial location, what type of injection it is, and then we set up the injection. Injection is nothing but the way discrete phase particles will come into the domain. We can define how it comes into the domain based on our equipment or practical conditions. These are the initial conditions for the particle size and distribution. Once we have defined the injections, next is to set up the boundary conditions related to the discrete phase. We can do this by going into the boundary conditions panel and giving the boundary condition for discrete phase under each boundary. The different boundary conditions available for discrete phase are reflect, trap, escape, wall jet, wall film, as well as user defined. Depending upon what exactly occurs near that boundary, we can give different boundary conditions to cover various phenomena associated with discrete phase near the wall or near the boundary. Once we have defined the boundary conditions, we also define the material properties. Now, whenever we turn on the discrete phase model, a separate material will appear in our materials panel. We can change the properties of that discrete phase material by clicking on that material and editing it. The final step is to initialize our solution. For this, we have to give the initial conditions for the continuous phase flow. Once we initialize the solution, we can proceed with solving the problem. Now the last step is to begin our solution. For this, we go to solution method and solve. Then we select the solver schemes. That is, we select whether we are going to use which type of pressure velocity coupling that we are going to use. We select volume fraction schemes if we are using multi-phase models. Then we set the URFs, that is under dissection factors. We set the monitors, that is what type of parameters are we going to monitor during our calculations. And then we finally solve, that is we press on this calculate button in order to begin our solution. I would like to say thank you for viewing this particular lecture. If you have any doubts, you can always contact us. So thank you for viewing this lecture and see you in the next lecture.